Hi everybody. In this video we continue with chapter 15, probability distributions, specifically 15.5, expectation algebra. So here we have a table with a random probability distribution. So if we want to find the expected value, remember that that is just the mean. So that means each probability times the x value. And we add that up. So this gives us 3.1 as the mean or expected value. But what happens if we want to add 3 to each one of these terms? What would be the new expected value? Now, intuitively, you probably would guess that the mean would just be now 3 units to the right, so 6.1. But let's verify that. So that means that this is going to be now 4, this is going to be 5, 6, 7, and 8. So the new expected value would be given by this sum. And this effectively will give us 6.1. So in other words, notice that this means that the expected value of x plus 3 is going to be equal to the expected value of x plus 3. Now, what would happen if we multiplied each x value by 4? What would happen to the expected value? What would happen to the mean? Intuitively, we would think that the mean would increase by a factor of 4, but let's verify that. So this number here would be 4. This would now be 8, 12, 16, and 20. So let's find the new expected value. And this would give us 12.4. But you can tell that 12.4 is simply 4 times this. So in other words, that means that the expected value of 4 times x is going to be 4 times the expected value of x. Now notice if we draw a histogram of the first table, we have the distribution represented here to the left. Now what happened when we shifted every value 3 units to the right? Notice that the histogram simply shifts 3 units to the right, but that does not affect the variance. The variance would be the same because each value is still distributed the same way as it was originally. The only difference is that it shifted 3 units to the right. So that means that the variance of x plus b is the same as the variance of the random variable x. Now, what would happen in this case, the last one, where we multiplied each of the variables by 4? Well, notice that now instead of 1, 2, 3, 4, and 5, our x values are going to be 4, 8, 12, 16, and 20, and their probabilities will remain the same, but the variance has definitely changed by a large factor. Now, we don't know what that factor is yet, but in the next slide, we're going to go into this a little bit deeper. So in the next slide, you're going to find the proof of what we just did. First of all, for the discrete case. So notice that here they're doing both simultaneously. It's the expected value for a constant a, times a random variable x, plus a constant b. So we translate that into a sum, and then notice that we can distribute the probabilities, and then we can separate the sum in sigma notation. Notice that after that we can take out the constants a and b. But notice that this is a times this, which is just the expected value. And then it's B times this, and this sum is the sum of the probabilities, which is just going to be 1, as we can see here and here. So in the end, we get that this is going to equal A times the expected value plus B. Now you can look at the continuous case, which is the same thing, but in terms of integration. Let's recall that for the variance, the definition is the deviations from the mean squared times each probability. And then we had spoken about deriving this formula. Now, in case you don't remember how we get from here to here, just think of it in this way. If we have the sum of x minus mu squared times each probability, we can expand this, right? So this would be the sum of x squared minus 2 mu x plus mu squared times the probability. And then we can just distribute this and separate the sums. So notice that we can rewrite this as the sum of x squared times p of x. And we can write this as minus 2 mu times the sum of x times the probabilities plus mu squared times the sum of px. But let's notice two things here. First of all, notice that this here is simply the mean or the expected value, right? So this is just the same as mu. And this expression here is just the sum of all the probabilities, which is equal to 1. So we end up with the expression, the sum of x squared px minus 2 mu squared plus mu squared, and then we end up with the final expression, right? Which is the same as this over here. Now for the continuous case, you can try it out yourselves, and it's going to be exactly the same procedure, but using integration. Now, let's take a look at the variance of a linear function of x. That means what happens if we multiply the random variable x by a constant a, and we add a constant b. So notice that here we define y, capital Y, as a times the random variable x plus b, which in the specific cases can be written as y equals ax plus b. By specific cases, I mean for the individual variables. So notice that we can write this by definition as the difference here. Notice that this is the difference between each y and the mean squared times the probability of y. But if we rewrite this in terms of x instead of y, notice that this y here equals this, and then this is simply the previous definition that we found in the previous slide, where the expected value of ax plus b is going to be a times the expected value of x plus b. In this case, it says minus because we have a negative sign in front. So notice that from here, we're going to get that the b's cancel out, and we get this expression by factoring out a. And notice that a would be a squared when we factor that out. And since this is a variance, so that just means that the variance of a times x plus b is equal to a squared times the variance of x. So remember in the first example, we said that the variance was going to be modified by some factor that we didn't know, but now we can see through this proof that it's going to be the constant that is multiplying the random variable x squared. So we continue with linear combinations of random variables, and we're going to take a look at example 15.25. And it says, you have a large box containing equal numbers of chips with the numbers 0 and 1 on them. You draw one chip, record the number, and return it to the box, then draw another chip and record the number. Part A. Find the expected value and variance of the sum of the numbers you record. So for part A, they want us to find the variance and the expected value of the sum of the numbers recorded. So we can refer to this as z, which is dependent on x plus y. So for this, we would have to create a table and analyze a few things. So here's our table. And notice that in the first column, we have the possible results for z. You have three probabilities. You can get 0, you can get 1, or you can get 2. Now, how can you get 0? Only if you draw 0 from the first chip and 0 from the second chip. How can you draw 1? If you get 1 from the first chip and then 0, or if you get 0 and then 1. And then there's only one possible way to get 2, which is 1 and 1. So notice that you can look at this in two different ways. We have 4 different outcomes, and there's only one possible outcome here. That's why the probability would be 1/4. Or you can look at it this way. You can say that the probability of getting a 0 is 1/2, and then getting a 0 again is another 1/2, so the multiplication of that would be 1/4. Likewise, we have 2 ways of getting 1, so that means that this represents 1/2 of the possible outcomes. And the other way to look at it is by just multiplying the probabilities, 1/2 times 1/2 plus 1/2 times 1/2. And that's going to give you 1/2. And then 2, getting 2, there's only one way of that, so that would be 1/4 of the entire possible outcomes. And again, the other way of doing it is just going 1/2 times 1/2. So they want us to find the expected value of this, right? So let's remember that the expected value of, let's say this is z, so the expected value of z is going to be the sum of the z's, the possible z's, times the probability of getting z. So notice that this is going to equal, and this gives us 1. Then they want us to find the variance. So the variance for the random variable z is going to be equal to the sum of z squared times the probability of z minus the expected value for z squared. So notice that this is going to be, and this will give us 1/2. So now let's focus on part B. So for part B, they want us to find the expected value and the variance of the difference of the numbers you record. So this requires a totally different table. So notice what would be the possible outcomes. We could get either 0, we could get 1, or we could get -1. Now we have 2 ways of getting 0. 0 minus 0, or 1 minus 1. There's only one way of getting 1, which is 1 minus 0. And there's only one way of getting -1, which would be 0 minus 1. So again, this would be 1/2 of the outcomes. This would be 1/4 of the outcomes. And this also is 1/4 of the outcomes. If we apply the mathematics, these would be the operations. So again, the expected value, in this case, let's say that the event is z, and this is equal to x minus y. So in this case, the expected value for z will be, and this will give us 0. And for the variance, and this equals 1/2. In the next slide, you're going to find a very important property of expectation algebra. Now notice that if x and y are any two random variables, then number one, the expected value of a constant a, times a random variable x, plus or minus a constant b times the random variable y is going to equal a times the expected value of x plus or minus, depending on this here, plus or minus the constant b times the expected value of y. And then, very importantly, if the two variables are independent, then the second property applies, and that is that the variance of ax plus minus by is equal to a squared times the variance of x and plus, always plus, b squared times the variance of y. So note that we add the variances regardless of whether the variables are added or subtracted. So next we have example 15.26, and it says, consider the two random variables x and y, where x is the number showing when we roll a tetrahedral die and y is the number showing when we roll a cubical die. Work out a, the expected value of x and the variance of x, b, the expected value of y and the variance of y, and c, the expected value of x plus y. So here we have the probability distributions for x and y. So tetrahedral means four sides. That's why we have four possible outcomes, and each has a probability of 1/4. And then the cubical die is the one with six faces, so six possible outcomes with a probability of 1/6 for each. Okay, so you guys already know how to find the expected value and the variance, so you should work it out on your own. For A, you should get that the expected value for x is going to be 5/2. And the variance is going to be 5/4. For B, the expected value for y is going to be 7/2, and the variance is going to be 329/12. Now for part C, what's the easy way to do it? Well, the easy way to do it is by following the property that we saw in the previous slide. And that is that the expected value of x plus y is equal to the expected value of x plus the expected value of y. So this is just going to be 5/2 plus 7/2, and this would give us 6. So now what is the long way? Notice that you would have to do this process, which is finding all the possible outcomes for x plus y. So you can get 2, 3, 4, 5, 6, 7, 8, 9, and 10 as the sum. And then all the different ways in which you can get these. So there's one way to get 2, there's 2 ways to get 3, there's 3 ways to get 4, there's 4 ways to get 5, 4 ways to get 6, 4 ways to get 7, etc. And then you would have to multiply all these different combinations times the probabilities, and you would end up with this table. Now, notice that if you calculated the expected value from here, the expected value of x plus y, this would also give you 6. But notice how the process is shortened very much by this property. So in the next slide, you're going to find something that is called an interesting application 1. And basically it's this. If x1 all the way to xn are observations of the same random variable x, then this relationship is true. The expected value of a1 times x1 plus or minus a2 times x2 plus or minus all the way to an times xn would equal this here. In other words, the sum or subtraction of the constants that multiply each random variable x times the expected value of x. Then they talk about special cases when you have the expected value of random variables that don't have any constant multiplying them, or you can say the constant is 1. That would just be equal to, um, in this case, 2 times the expected value. And in general, n times the expected value, depending on how many independent variables are added. And then there's a second case. If these observations are independent of the same random variable, then for the variance, you would have that each one of these constants that multiplies the independent variables would be then equal to these same constants squared and added regardless of whether you added them or subtracted them before. Notice that you would add them or add their squares and finally multiply that by the variance. The other special case, now this is interesting because we're going to apply this in the next example, where you have the variance of x1 plus x2, that's going to be 2 times the variance of x. Now, if x and x are not independent, they're not independent, like here, the variance of 2 times x, then this wouldn't apply, right? This would be false. It wouldn't be equal to this. It would be equal to the square, in this case 2, so 2 squared times the variance of x. Then they say, well, this is a special case for this as well, where a is 2 and b is 0, the linear case that we saw before. Now we can generalize the results. Notice that for the first part, we would get n times the variance of x. That is, again, when these are independent observations of the same random variable. If they're not independent, then we get n squared times variance of x. So next we have example 15.27. And for part A, it says, throw an unbiased cubic dice and define the random variable as the number on the upper side of the dice. Calculate the expected value and the variance of this random variable. So here is the probability distribution of the related random variables. So notice that in this first row, we have the possible outcomes, which range from 1 to 6. Then the probability of each outcome, which is 1/6 for every one of them. And then the expected value would be the variable times its probability. And we have this in this row. And then we have the sum. So this is the expected value. And then in this case, it would be the square of the variable times the probability, right? So notice that it's just 1 and then 4 times the probability, 9 times the probability, and so forth. And this is their addition. So in the end, we get the variance by subtracting the expected value squared from this other value, and we get 35/12. Okay, so for part B, it says, throw 2 unbiased cubic dice and define the random variable as the sum of the numbers on the upper side of each dice. Calculate the expected value and the variance of this random variable. So notice that we could define this as y is equal to x1 plus x2. Now notice that these are independent observations of the same random variable x. So we would have that the expected value of x1 plus x2 is just going to be 2 times the expected value of x. In other words, 2 times 7/2, which is going to be 7. Then for the variance, now notice that in this case, because the observations are independent and they are of the same random variable, this is the same as saying variance of x1 plus x2, and this is just going to be 2 times the variance of x, which in this case is going to be 2 times 35/12, and this equals 35/6. For part C, it says, throw 1 dice and define the random variable as twice the number on the upper side of the dice. calculate the expected value and the variance of this random variable. So notice that we could define this as y is equal to 2 times x. And this is not an independent observation, but that doesn't affect finding the expected value. That would just be that the expected value of 2 times x is 2 times the expected value of x. And in other words, we would get 7 again for this expected value. But with the variance, things change, right? The variance of 2 times x is going to be 2 squared times the variance of x. And this is going to give us 4 times 35 over 12. And this equals 70 over 6, or 35 over 3. So next we have example 15.28. And it says, in a multiple choice quiz of 10 questions, each question provides 4 choices, one of which is correct. A student is guessing on all questions. Part A, find the expected value and variance of the number of questions answered correctly by the student. So notice that this is a binomial distribution. And in this case, there's 10 trials. And the probability of success is, because there's 4 questions, is going to be 1 out of 4. So 0.25. And then the probability of failure is going to be 0.75. So the expected value for x in these cases, remember, is going to be n times p, which is 10 times 0.25, or 2.5. And then the variance of x is going to be n times p times q, which is 10 times 0.25 times 0.75, and this is 1.875. For part B, it says, set up a table showing the probability distribution of the number of questions answered correctly by the student. And for C, use your table to calculate the expected number and variance of the number of questions answered correctly by the student. So let's take a look at a table. So here's our table, and notice that here we have the possible outcomes. 0, 1, 2, 3, all the way to 10, right? 10 correct ones. Now, here they're applying the PDF to find the probabilities. N over X combination, right? And then we had P to the X times Q to the N minus X. So using this formula, you would find these probabilities. Now notice that here they have 0, but that's not correct. The thing is that they rounded, but if they had used at least 5 decimals, this would be accompanied by decimals and it wouldn't be exactly 0. But since they rounded, they still got 1 as the total for the probabilities. And once they multiplied the probabilities by each possible outcome and then added them up, you get the same expected value of 2.5. And then they squared them and multiplied them by the probabilities, meaning they squared the variables, multiplied them by the probabilities, added them up, got this, then applied the formula for the variance, and they also get 1.875, which would agree completely with the theoretical values from part A. So now let's take a look at D. For part D, it says, the teacher will give a score of 3 marks for each question answered correctly and will not penalize wrong answers. Find the expected score and variance of the scores of the guessing student. So in other words, this event y is equal to 3 times x. So the expected value of 3 times x is going to be 3 times the expected value of x. So 3 times 2.5, and this is 7.5. Then the variance of 3x is going to be 3 squared times the variance of x, and this is going to be 9 times 1.875, which would give us 16.875. For part E, it says set up a table for the distribution of scores of the student and use it to calculate the expected value and variance of the scores. So let's go to the table. So here's the table for part E, and notice that y is equal to 3 times x, so we get these new values for y, right? 0, 3, 6, 9, all the way to 30. The probability of each one of these occurring, once you multiply the probabilities times the random variable and you add them all up, you're going to get, again, 7.5 for the expected value. And you also get 16.875 for the variance. So in the next slide, you're going to find something labeled Interesting Application 2. And they're talking about the expected value for a mean and the variance for a mean. So it turns out that the expected value for a whole group is just going to be the expected value for one individual. And that the variance of the mean, or the variance for the whole group, is going to be the variance for one individual divided by the number of people in the group. So next we have example 15.29. And it says, in a multiple choice quiz of 10 questions, each question provides 4 choices, one of which is correct. So this is the same as the previous example. A correct answer is worth 3 marks. A randomly selected group of 36 students who are not familiar with the topic are all guessing on all questions. Part A, find the expected mean score for this group. So this is the same as saying that the expected mean score for the whole group is going to be just the mean for an individual. And we've had found before that this is equal to 7.5. For part B, it says find the variance of the mean scores for this group. So the variance for the mean scores, we said this is going to be the variance of an individual divided by the number of individuals. And this is going to equal 16.875 divided by 36, because there's 36 students here. And this would give us 0.4685. Okay, then we have C. It says you are told that the distribution of scores is normal. So it's a normal distribution. What is the probability that a student in this group scores at least 9 marks? So that means the probability that one student scores at least 9 marks. So we need the calculator for this. So here we go. We have to go to distributions and the normal cumulative distribution function. So remember that for these functions, the first thing we need to do is put in the lower bound. So the lower bound here is 9, then a comma. The upper bound would be 30 because that's the maximum amount of points that are possible. Then we have the mean, which is 7.5, and the standard deviation. But the standard deviation is just the square root of the variance. So we would do square root of 16.875. Hit enter, and there we go. So notice that this is going to equal 0.3575, or a chance of 35.75%. Then for D, it says, under the same conditions as above, what is the probability that this group's mean? So now it's the group. is at least 9 marks. So the probability for the group mean to be greater than or equal to 9 marks. So back to the calculator. So again, we go to distributions, the normal cumulative distribution function, and same thing, right? So the lower bound is going to be 9. The upper bound, oops, it's got to be a comma. The upper bound is still 30. And then we have that the mean is also 7.5. But what changes is the standard deviation, because now the standard deviation is going to be the square root of the variance we found in part B, which is 0.46875. So we hit enter, and we're going to get 0.0142, or around 1.42% chance. So in the next slide, you're going to find linear combinations of normally distributed random variables. And it refers to a very significant property of normally distributed random variables. And that is that a linear function of one of them, or a linear combination of several, is also normally distributed. So what does that mean? That means that if x is a normally distributed random variable with a mean mu and a variance sigma squared, then y equals ax plus b will also be normally distributed, and it's going to have a mean that is equal to a times mu plus b. This is a property we saw in the previous section. And the new variance is going to be a squared times the variance of x. Then there's also the case that if x and y are two normally distributed random variables, then z, defined as a times x plus or minus b times y, would end up having a mean that would be the addition or subtraction of the means of x and y, depending on this, right? You either add or subtract, depending on this here. But the variances are always going to be added, and this would make up the new variance for z. So next we have example 15.30, and it says, test scores in an HL class are to be curved as follows. Every student will receive 5 marks, which are then added to twice the score on the test itself. Given that the test scores are normally distributed with an average of 35 and a standard deviation of 7 marks, find part A, the mean and standard deviation of the curved score. So notice that we can define y as the new curved score. So that would be equal to, y is equal to 2 times x plus 5, where x is the actual score on the test itself. So notice that they're giving us a mean of 35 and a standard deviation of 7. So the expected value for y is going to be 2 times mu plus 5. In other words, 2 times 35 plus 5, and this gives us 75. Then we have that the standard deviation is 7, therefore the variance is going to be 49. So the variance for y is going to be 2 squared times 49, and this is going to give us 196. And if we square root that, it's going to give us that the standard deviation is 14. For part B, they want us to find the probability that a student receives a score of at least 65 after curving. So that means the probability that y is greater than or equal to 65. So for this, we're going to need the GDC. But first, let's define a few things. Now, notice that the lower limit here, for this case, is 65. The upper limit is not going to be 100 because somebody could score 100 on the test itself. So that means that the upper limit is going to be 2 times 100 plus 5, which is 205. And then, well, we have that the mean is 75 and the standard deviation is 14. So let's now go to the GDC to calculate this probability. So again, second variance, we go to distributions, and number 2, the normal cumulative distribution function. And then we're going to have that the lower limit is going to be 65. We have that the upper limit is 205. We have that the mean is 75. And the standard deviation is 14. So now we hit enter, and there is a probability. So it's going to be 0.7625, or 76.25%. So next we have example 15.31, and it says, wooden barrels are traditionally used to store pickled cucumber in some European countries. To hold the wood together, steel rims are fixed around them to keep them tight. To keep the steel tight around the wood, the rings are slightly smaller in diameter than the barrel, heated so that they expand slightly before being fitted, then allowed to cool. The diameter of one type of barrel is known to have a normal distribution, with a mean of 56 centimeters. So for the barrel, we have a mean of 56 and a standard deviation of 0.20 centimeters. So if the standard deviation is 0.20, that means that the variance is going to be 0.04. The rims are constructed so that they yield a diameter that is also normally distributed, with a mean of 55.70 centimeters. So for the rims, the diameter has a mean of 55.70 and a standard deviation of 0.30. So that means that a variance of 0.09. And this is at room temperature. The rims are heated so that the diameter increases by 1.5%. Part A. What is the probability that a randomly chosen rim will fit around a randomly chosen barrel without heating? Okay, so basically what we need here is for the diameter of the rim to be greater than the diameter of the barrel. In other words, the difference should be greater than 0. So let's name this new normal distribution as y equals r minus b. And this will be normally distributed because r and b are also normally distributed. So notice that the expected value for y is going to equal the expected value for r minus the expected value for b. And this is going to be 55.70 minus 56, which is going to be negative 0.3. Then we need the variance. Notice that the variance for y, and we always add the variances, the variance of r plus the variance of b. And this is going to be 0.09 plus 0.04. And this is going to equal 0.13. So the probability that we want to find is the probability that r minus b is greater than 0. In other words, we need the area under the curve for the normal distribution with a mean of minus 0.30 and a variance of 0.13. So for this, we're going to need the calculator. So again, we go to the cumulative distribution function, and that's number 2. So here, the minimum is going to be 0, and the maximum is going to be the mean for the rim, so 55.7. The mean is negative 0.30, and the standard deviation would be the square root of 0.13. So we hit on enter, and there it is. The probability is going to be equal to 0.2027. So that's about 20.27%. So now let's work on part B. So for part B, it says, what is the probability that a randomly chosen rim will fit around a randomly chosen barrel with heating? So notice that here we would have to define a different variable. Now, this one would be equal to a 1.5% increase with the heating for the rim. So that means 1.015 times R. And we would have to subtract from this the barrel, the diameter of the barrel. So the expected value for H is going to equal 1.015 times the expected value for the rim minus the expected value for the barrel's diameter. And this is going to be 56.5355 for the expanded rim minus 56 for the barrel. And this is going to give us 0.5355. Now for the variance, notice that we have this number now multiplying the first diameter. So the variance for H is going to be 1.015 squared times the variance for the diameter of the rim plus, because with variance we always add, plus the variance for the diameter of the barrel. And from here, we are going to get 0.0927 plus 0.04, and this is equal to, rounding, 0.133. Okay, so what they want us to find is the probability that the diameter of the rim that is expanded 1.5%, so 1.015 R, minus the diameter of the barrel is greater than 0. So for this, we will need the GDC again. So again, we go to distributions, number 2, and here the lower limit is going to be 0, but this time the upper limit is going to be the expanded rim, which we said would be 56.5355. Then we need the mean, which is 0.5355, and we need the standard deviation. So that means the square root of the variance, which we found that was 0.133. So we hit enter, and we get 0.92, let's say 9. So it's a 92.9 or 93% chance that it will fit.